Today we are going to do Lab 14, which we are gonna make a Sobel filter, and then we use the things that last week we used. We put our HLS IP onto the pynq Jupyter notebook. Then we use this IP using Python as a driver. So here is all files we're gonna use for this lab, and these two are the HLS source code and the test bench. And this folder contains the pynq driver, the Python code, and the test image. So let's first create a project. We will call it Sobel. In the same folder that contains this file, and add our source code. Choose the top function, Sobel function. Add the test bench. Choose our pynq board. Okay, so let's check our source code first. So here is the source code for our Sobel filter. We here use the 3-line buffer instead of whole frame buffer because we don't have such large space on the pynq, and this is input image, output image, and the interface we choose to use XI memory. And here I pack the memory pixel into the RGB form, like here. Each RGB pixel contains 8 bits, but we pack this to the 32 bits for convenience. And actually, using Sobel filter, you don't need whole RGB 3 channel. You can only transfer the gray channel. For the consideration of later application, I think maybe I'll make it as a RGB for you to use this code as an example for your later project. And okay, we run C simulation. Here is our input. I simply set the image 4x4, a very small image, to just check it. And these values are the RGB channel 10, and all of them equals to 10, 20, 30, such like. And this value will first convert to grayscale, then apply Sobel filter on it. Results to our function is here, and this is a golden result, and it should be have no error. Next step, we run C synthesis. So the synthesis is done, and we can export our IP. is also finished. So next we can check the IP here. It's in this folder, and you can check this file sobelinfo.xml to check some information. As our function, we have 4 arguments: input image, output image, and the width and the height. Here we need this information for later we coding driver on the Jupyter notebook. We need this address for example, this argument is w, which means width, and it has a address 0x28. Yeah, we will need this value later. But the next step, we continue to use Vivado for our block design. Create a new project. I'll just call it Sobel pynq. And in the same folder, which have our source code, click next. Choose our pynq board. And first we gonna add our HLS IP. So this folder contains the HLS project. Open it, implementation IP here. Select this folder. So you can here see this IP is now added to our project. Next step, we create a block design. I'll name it Sobel pynq. And add our pynq, and then add our Sobel filter. And the next step, you double click your pynq block and goes to PSPLO configuration and open a sleeve interface. Open XXI HP and check the box of XIHP0 FPD. This interface is the DDR interface for our PS, which means the processor is our pynq side, and the PLO means the programmable logic is our FPGA side. We open this interface so that the FPGA side can read image through the DDR interface, direct access to the DDR, and get the image data. Okay, click OK. Now we have additional ports here, and click Run Connection Automation. Select all. And run this. And run this again. Select all. Now here's our design. You can verify. It should have no error. And the next step, we create a HDL wrapper. Okay, and click generate bitstring. It's gonna take a little while. Here we complete the generate bitstring, and we now export the block design. Okay, so we are gonna need 3 files. We create a project, create a folder and then overlay. overlays, and we're gonna need the base string file, implementation 1, and base string file. Copy here, and next we gonna need the TCode file. This is our block design, and the next thing is this file. So we renamed all three this file to Sobel. Okay, the next step, open your pynq. Gotta give it a minute. Okay, now the pynq is opened. We can connect to the pynq and click settings. If your first time connect to pynq using this method, you may have to type the password. The password and the username are both settings. So now open this folder and open pynq. You open overlays, and here you can. This is the previous project I've done, so you can ignore that. You can create a folder named Sobel and copy all these three files onto our board. And the next step, we copy our Jupyter notebooks to the board. So this folder is our Jupyter notebook files, and then we create a folder named Sobel. Copy these two files onto the board, and now you can open this link to connect to your pynq Jupyter notebook server. And here, so this folder is our driver that we just upload. You open this Jupyter notebook file. Here contains the Python driver to use the FPGA IP, and this folder contains the test image. And we delete this file first. Okay, so click run selective file, select cells. This step imports some libraries we're gonna use it. And this class, this object, is the driver I wrote for our FPGA IP. You can modify it if you want. So let's check the code first. This this objects initialized by this overlay path, and this overlay which is imported from here, and so this is our overlay. Then to get our IP, we can just select the overlay dot and your IP name, which is Sobel/0. You can check this in your block design. Here you can also rename it if you want. And here we get our overlay and our IP. And next step, we allocate DDR memory for the image. For image data, let's check this function. This function allocates physical continuous buffer for our data. This in buffer and out buffer is not actually a array. This is a address. So we use this function, which is built in this library, to allocate the size, the shape, our max pixel. We set it as list size and uint32 data type. And these two lines initialize our buffer to 0. And we check the next line, this run function. After we allocate our DDR memory, you can set the image. The input is an image. You can use OpenCV or whatever else you want. And let's check this function. The image, you get the height and the width, and calculate the total pixel of this image, and check if the pixel number exists. And this function converts our image data structure to the buffer structure that we want. As we mentioned earlier, in our IP, the input data structure should be a form like this, which is packed to a 32-bit data and has RGB channel. Now we need to pack the whole image into this data structure. Check this function. First, we split our 3-channel RGB, and our channel should shift left the 16-bit and 8-bit for green channel and bit. Then, so this is our data structure for our buffer, and should be flattened. So here is our buffer containing our image. Next step, you put this image data into the in buffer, which is the DDR memory. You copy this data to a DDR, and then we call this method to make it from the processor side to the DDR, to make this data goes from processor side to the DDR memories. And then you send the argument to the IP using write method. And this address is mentioned earlier in this file. You can check the address. Okay, so we send our in buffer physical address, out buffer's physical address, and the width and the height. Next step, you write the 1 bit to the IP, which means it should start. And this line is it keep reading the port, the AP down port, until the IP complete the computation. And next step, we move the DDR memories data back to our processor using this method. And so this output buffer is actually contains our image data, but this is in the buffer form. We need to convert it back to the image form. So this function I wrote to unpack the buffer and made it OpenCV-like form, which is BGR order, in the BGR order, and it returns the result. So let's see the let's run this block and run this block. This block read the image and then send to the IP. This is the method we mentioned before. So let's just run it. So we can now see here is save the result into the JPG file. We can open it. So yeah, this is the correct answer. And you can delete this object to release the buffer resources if you want. Yeah. So this is our Lab14.